Hi, I'm Scott Wing. I'm in the Department of Paleobiology here, and I came up out of the Carolina League in 1984. We humans have changed the planet substantially over the last 150 years, driving up atmospheric carbon dioxide and increasing average global surface temperature by more than 1 degree Fahrenheit. We're quite certain that temperature will continue to rise through the 21st century, though predicting how much the planet will warm is a lot harder. There are 3 scenarios in the red lines on this graph from the Intergovernmental Panel on Climate Change, and model projections like these are getting better all the time, but as a paleobotanist, somebody who studies fossil plants, I take a historical perspective. I want to know if there are examples of past climate change that are similar to what we are experiencing now. What happened to plants then, and can fossils help us anticipate the future? To find an analog for human-induced climate change, you have to go back a long way. For the last 800,000 years or more, Earth's climate has seesawed from glacial to interglacial, but CO2 has been below current levels, and the temperature has not been warmer than at present. There's no precedent for the future in the geologically recent past. But if we squash those 800,000 years to the side of this graph and look back 70 million years, you can find high CO2 and high temperatures back in the Eocene, before 35 million years ago. Within this extended period of warm climate, there's a notable sharp spike that you can see at the very top of the graph there of even greater warmth called the Paleocene-Eocene thermal maximum, or PETM. And I'm going to expand that out. This was a hot spell about 56 million years ago that was kicked off by the release of an enormous amount of carbon, about the amount contained in our present-day fossil fuel reservoirs. It's a geologically short period that followed that, in which global temperature rose by 7 to 14 degrees Fahrenheit, and that heat wave lasted for at least 150,000 years. For more than 30 years, I've spent part of each summer collecting fossil plants in Wyoming, trying to read the history of what happened to plants during the PETM. And by the way, I might add that this is a project that only a forever place, as the secretary says, like the Smithsonian, would tolerate. I've collected, through that time, a lot of fossil leaves, a lot of beautiful fossil leaves, and I've collected 100 sites spanning the roughly million years around the PETM, with now few gaps that are longer than about 20,000 years. These are just piled up. The end of each X is a site, and they have the ages that are shown on the x-axis. The record shows a fascinating pattern of change. Many species that lived in the area for millions of years, and you can see those in the lower part of this graph, are absent from the PETM. So these are plants that lived there for a long time. They're missing from the pink band where the PETM is. And many species that are present during the PETM are present only during the PETM. Those in the upper part of the graph, they aren't found before or after. Well, who were these plants? Before the PETM, birches, sycamores, katsura, and dawn redwood relatives dominated the vegetation here. During the PETM, the key players were members of tropical plant groups, including many in the bean family. And after the PETM, the natives came back again. What might the landscape have looked like? Well, we've worked with an artist at National Geographic to reconstruct this, and so that before the PETM, it might have looked something like the Okefenokee Swamp, although with ginkgos and strange animals. During the PETM, more like a dry tropical forest in Mexico, and after the PETM, back to the Okefenokee Swamp look. What have we learned from all this work? Well, first of all, we know that a big carbon release gives a big temperature increase. Very simple. The climatic effects of that carbon release lasted 150,000 years. The plants thought it was drier as well as hotter. Plants definitely think. Climate change coincided with a nearly total extirpation of most plant populations and a replacement by different kinds of plants. So extirpation, local extinctions of populations, not species, and there wasn't much extinction on a global scale. Where do we go from here? Well, it's taken most of my career to assemble the fossil record that you see here, and some on either end that I'm not showing you. And our record is miles better than anybody else's record of this time period. But these gaps that you see between those X's are still on the order of 20,000 years, and that's really a killer for what I want to do. 20,000 years doesn't seem like much time to me, but I've noticed that others don't feel that way. And to make the PETM really useful for predicting our own future, we need to be able to describe events that took place over centuries, not tens of millennia. Particularly, we want to know how fast climate and plant communities changed at the onset of the event. Was the amount of extinction low because even that rapid change at the beginning took 10,000 years, say? A few years ago, two colleagues and I initiated the Bighorn Basin coring project, and in 2011, we dragged drilling rigs out to the Badlands of Wyoming chanting "Drill, baby, drill," and extracted cores of pristine, unweathered rock. Last winter, we sampled those cores at a level of time resolution that we really had never dreamed of before, taking samples every few centimeters, just a few hundred years apart, but all of them 56 million years old. The cores are too small to preserve leaves, but they do preserve chemical fossils, traces of the molecules that compose the plants and animals that lived during the PETM. And so I think the search to understand the PETM and our future will go forward using these new tools, and that fossils will play an important role in helping us understand how our actions are going to affect the planet that we live on in this dawn of the age of humans. Thank you. Well, within my lifetime, maybe not so much. The question is, what will happen in our lifetimes? I think that the changes have already begun, and they mostly take the form of extreme weather events. Those become more and more common. But my grandchildren or great-grandchildren, if such a thing were to happen, will be born in a planet where the composition of the atmosphere will be more like it was 45 million years ago than like when I was born.
And what was that like?
It was very high CO2 and a very hot planet with a lot of energy from all that heat driving very big storms. Yeah?
What do you think the latitudinal thermal gradient and the diversity gradient look like in the thermal max?
The question is, what does the gradient of diversity, biological diversity and climate look like from the equator to the pole during these really warm times? And we know it's very much more shallow. So the difference in temperature between the equator and the pole is less than it is now. And that the effect of that on the gradient of biological diversity is something that we're still trying to work out. But it looks as if there is more diversity of life near the poles during these really warm times. What we're not clear on is whether there's as much diversity at the low latitudes. When it gets really hot, it may make things tougher in the tropics.